Okay. All right, we'll see. Thank you. I see what the strange one, but you need to be able to handle questions like these. They say we need to cover K from 1 to 25, but there's no K in the general term. So guys, that's the thing that each term is 10, right? If there's no K that you can sub in, then every single term is just going to be that number. Now you could have seen this as an arithmetic series or a geometric series, right? Because if this is an arithmetic series, your first term is A and you're just adding 0 each time, so the difference would be 0. Or you could say it's geometric, your first term is A and your ratio is 1, all right? But if you do that, guys, if you have a ratio of 1, you're going to get 0 in the denominator of that formula, right? Which is actually not going to work. So I'm hoping that this makes sense. Do we agree that going from 1 to 25, they are 25 terms? Right, so that's clear to everyone. Now, if you just have 25 tens in a row and you're adding all of them together, can't you just say 25 times 10? Right? Does that make sense? We use this concept in actual proof, the first proof that we did, where we had a 2a plus n minus 1b and a 2a plus n minus 1b. We added a bunch of them to n terms and we put the n in front. You guys remember that in the first proof. Right? So if you have 25 in this case of the same number that you're just adding, you can just, instead of physically doing that, you can just say 25 times the number. Yes. I just Yeah, and it would have given you a 0 in your denominator. So if you're saying that this is a geometric series, then what are you multiplying by? By 1 every time. See, so then your r minus 1. That's going to be something to the root. So the r minus 1 will be 1 minus 1, which is 0. Okay, so you actually can't use that formula for this one. Yeah, because this is normally the general term. So the general term is just 10. So every single term is just 10. All right, for 6a there, you had to find, this was similar to number 8 that we learned yesterday. So they gave you term 1, which we all know is a, and they gave you term 4 as negative 12. And they said find terms 2 and 3 if it's an arithmetic series or sequence. So term 4, using the arithmetic sequence formula, will be a plus 3b. So this is exactly what we did yesterday. I even worked through it step by step. You put in your a value and then you solve for b. So term 1 is 3 over 2. You're supposed to minus 9 over 2 from it to get term 2. Then to get term 3 again, you must minus 9 over 2 from it to get the next. Not sure where that revision exercise came from. I always feel like it was someone set it by looking at questions in the textbook. So this question is identical to the one that we did. The values are different. The values are swapped around. They're exactly the same. Let's find this one. The next one was saying against term 1 is 3 over 2, against term 4 is negative 12. We must again find terms 2 and 3, but now it's geometric. So now instead of a plus 3d for term 4, we're going to write ar to the power of 3 for term 4. So we're using the geometric term formula. So you put your a value in there, that's equal to negative 12. If you take negative 12 divided by 3 over 2, you get negative 8. So then the cube root of negative 8 is just negative 2. Okay, so then to find term 2, you have to take term 1 times the ratio. That will give you term 2. And then to get the next term, you need to take term 2 times by the ratio again, which will give you term 3. And there was just an extra question in this one. They said now you must find the sum to 7 terms if this is a geometric series. So that means that you must use the geometric series sum formula firstly, and you must work with this ratio that we found. Okay, so it wasn't a completely new question, it actually followed on from B. Right, so using the value found in B, we now need to find the sum to 7 terms. So you can just see I just sub that into the formula. And guys, please, when this ratio is a negative number, you have to put the whole negative number in brackets when we raise it to any part. Okay, if it's just a 7, that's fine, but if this was a whole, not a whole, sorry, an even number, it would have changed the value. Okay, so it is important that we put that whole ratio in brackets when we raise it to any part. Okay, any questions, guys? Moving on now to something new, the last section. So you can write infinite geometric series, that is the new heading. Okay, guys, I want you please to write converging series. Converging series. That is the first type that we're going to look at. You can actually write GS. It won't happen for an AS. It's not such thing. All right, the converging geometric series. Now, converging series, this will happen when your ratio is between -1 and 1. I'll show you an example now, but not 0. For example, we can have, say, the series 8, 4, 2, 1. Can we identify the ratio in that case? It's a half. Hey, do you see that I'm halving each time? So I'm going from 8, then it's 4, then it's 2, then it's 1. So my ratio in this case is a half. Let's just indicate that there. So I am timesing by a half, timesing by a half, timesing by a half again. So guys, let's continue this pattern. What will the next term be? What's 1 times a half? A half. What's the next term? A half times a half is a quarter. The next one? 1/8. I'm multiplying by a half each time, right? The next one? 1/16. Then 1/32. 1/64. And so on. All right, we can keep going. And what do we notice about the terms, guys? Do we see that they're getting smaller with each term? Each term is smaller than the previous one, right? Now I want you to try and, well, actually we can work it out, suppose. Let's try and just think about what's going to happen if we add these terms together, right? What is the sum to one term going to be? 8. Right, do we agree with that? The sum to 2 terms is going to be what's 8 plus 4? 12. The sum to 3 terms is going to be, so this one's 12, right? And now we're adding 2. So you see what I'm doing? I'm adding the first 3 terms together, so that will be 14. The sum to 4 terms, now I'm adding that 1, okay? That's going to be 15. the sum to 5 terms. Now I'm adding the next one. It's going to be 15.5. Hey, let's write it as 15.5. Because I want us to notice something as we're going up. The sum to 6 terms. Right, so now we have 15.5 and now we're adding a quarter to it. Quarter is 0.25, right? So that's going to be 15.75. Okay, I'm going to carry on here on the side. Now I'm going to start losing it. So now it's going to be 15, is it 875? Yeah. 15.875. Just double check that quickly on the calculator. I think that is correct. Okay, now I'm gonna surrender to this one. 15.875, and now we are adding the next one, which is 1/16. So that is going to give us 15.9375. The next one, sum to 9. So now I'm adding 1/32 to it. So that gives us 15.96875. Are we noticing something, guys? What's happening here? Yes, but also, does it look like it's approaching a certain value, perhaps? It's getting closer to 16, but it doesn't look like it's getting to 16, right? And why is that, guys? If we're going to add another term, I'm adding a smaller value, right? I think we have 10, is that correct? 5 and 5, yes. So that's the sum of all of them that we have now. Now, guys, if you add 1/128, you're still not going to get to 16. And if you then add 256, right? If you keep halving the terms that you're adding, you're still not going to get to 16, but you're going to get closer and closer to 16. All right, so we say that in this case, the sum to infinity will be equal to 16. And that is the new concept that we're talking about. Yes. Because every time, yes, but you're adding a smaller amount every time. So it's never actually going to push you over that 16. Okay, that's a real world example I always take in my classes. We're thinking of a tree, right? We're thinking of this tree maybe outside this window here. I don't know how long this tree has been here, but maybe in the first couple of years of the tree's growth, it grew quite fast, right? It looked like it was gaining height quite quickly. But then as it's getting taller and taller, this tree hasn't stopped growing, right? It is actually still growing. But the growth each year or each whatever kind of time period you want to talk about, let's say the growth each year is so small that it looks like it's not growing anymore, right? But it is actually still growing. So we would say that the height of this tree, which it is never actually really going to reach because it's almost like kind of done growing, but it is still growing. That final height is the sum to infinity. Okay, it's a bit of a conceptual thing, right? It's like an abstract concept, yes? Yes, yeah. So if we go closer and closer to that, yes, that's a so good example. It's almost like an asymptote, good. It would go towards that value, but it's not actually going to reach that value. Because of the type of ratio that we have, guys, do we notice that this means if the ratio is between -1 and +1, but it's not 0, you can see that this is a fraction. Right? Any number between -1 and 1, we're excluding 0. We're going -1 to just before 0, and then 0 to just after 0 to 1. Those would be any fraction. Okay, because if you are multiplying a number by a fraction, it is getting smaller and smaller each time. So the terms get smaller and smaller, which then has this effect, that the sum is approaching a specific value. All right, so we can add that here. Sum to infinity. The sum is getting closer and closer to 16. But never actually equal to 6. Guys, we're not going to have to do this calculation every time to find the sum to infinity. There is actually a formula that we can just use. And it's quite a simple formula. It is also on the formula sheet. So the sum to infinity, I want you just to write it down. The formula for that is A over 1 minus R. Definitely the simplest formula that we have done in a while. For converging. Yeah. So guys, you can only use this formula, you can only calculate the sum to infinity if your ratio is a fraction, like we just discussed, okay? So this only will be applicable if your ratio is between -1 and 1, but not equal to 0. Let's just discuss that not equal to 0 thing. Because 0 is between -1 and 1, right? But we have to now say that this is not going to work if R is equal to 0. If my first term is 8 and my ratio is 0, what are all my other terms after that going to be equal to? Okay, what is 8 times 0? 0. And then I multiply that by 0 again, I get a 0 again. So all of the terms after that first term will be 0. So guys, if you have that, if you have an 8 and a bunch of zeros, what is the sum going to be? Always just 8. Right, so this concept doesn't apply. There's no sum to infinity because then the sum is actually just the sum. All right, it's not a sum that will keep increasing slightly, keep getting closer and closer to a value. All right, so that's why we can't do this for 0. Now let's just quickly look at what happens when we have a diverging series. So diverging geometric series. So this is now when your ratio is either smaller than -1 or greater than 1. All right, so the exact opposite of when we had a fraction. So now, for example, if your ratio is -2 or +2, okay, we can test those two. We'll test when your ratio is 2. Right, and we'll start with an easy one. We'll start with the first term of 1. Now, if my ratio is 2, I'm multiplying by 2 each time, right? So my next term is going to be 2, and then 4, then 8, 16, 32, 64, and we can keep going. Guys, what's going to happen if I find the sum each time, just adding one more term? What's going to happen to that sum? And I get bigger and bigger, right? Because if I multiply by 2 each time, my terms are getting twice the size. My terms are getting much bigger. So if I have a sum to 1 term, it's going to be 1. Sum to 2 is going to be 3. The sum to 3 is going to be 7. All right, so every time you add the next term, the sum is going to get much bigger. So there is no sum to infinity with this type of number pattern because the sum just keeps increasing. All right, this kind of thing is not going to happen. It's not going to increase by such a little amount that it's getting closer and closer to a value. All right, so I'm just going to write here, red and red, the sum gets bigger as we add new terms. Therefore, does not approach a specific value. Therefore, does not have a sum to infinity. Okay, let's quickly do an example where r is -2, so we can just see what happens if it's actually a negative number. So if r is -2, and again we're starting with 1 as our first term. Now we need to multiply by -2 each time, right? Now 1 times -2 is -2. But then -2 times -2 is +4. +4 times -2 is -8. Right? So each time the sign is going to change. All right, -8 times -2 is +16. Then we're going to have -32, +64, and so on. Okay, now let's think what's going to happen to the sum. We actually start adding these terms together, right? So the sum to 1 is going to be 1. The sum to 2 is going to be 1 minus 2, which is -1. Then -1 plus 4, so if we do the sum to 3, is going to be +3. Then for the next one, we need to -8, so that's going to be -5. All right, then we're adding 16, so we're going into the positive again. Then we're -32, we're going into the negative. So the sum for this kind of series, where you're having, we'll actually put classes in between those, right? So the sum for this kind of series, where you're having a positive number, then a negative, then a positive, then a negative, then a positive, then a negative. The sum is going to almost like jump around, right? It's going to be a positive number, then it's going to be a negative number. Then because you're adding a bigger positive number, it's going to go into the positive again. Then because you're subtracting, right, a bigger number when you're minusing, it's going to go back into the negatives again. I'm not quite sure what the correct mathematical term is for that, but we say, can we say it will, the sum will go from positive to negative, is that fine? Okay, doesn't sound very scientific, but as long as we understand, the sum will go from positive to negative as we add more terms, so that will keep happening. Therefore, again, the bottom line is it will not approach a specific value. And that's what we are talking about when we're talking about a sum to infinity, where the sum is getting closer and closer to one specific value as you are adding more terms. Guys, they might try and trick you. They might give you a series where the ratio is of this form, where it's either a number that's bigger than 1 or a number that's smaller than -1, and ask you to find the value of the sum to infinity. And what's even worse is if you sub the values into this formula, you will get an answer. All right? But you need to recognize that if your ratio is not between -1 and 1, then you actually can't find a sum to infinity. All right? So I'll do an example now, but what you're going to write then, when you see your series and you identify the ratio, if you see that the ratio is not between -1 and 1, then you literally have to write sum to infinity does not exist. Okay, that will be your answer. All right, and they might ask you that to try and trick you. Okay, so let's do some examples just of actually using this formula. We're going to prove the formula. The two proofs that we've done, those are the only two that you need to know for this chapter. So we're not proving this one. Okay, let's do some examples. Okay, sorry, I was just looking through there. Okay, that's a bit small. I'll just zoom in. Okay, we can't find a sum to infinity for an arithmetic series either. Okay, because an arithmetic series is adding a number every time, so the terms will get bigger, or you're subtracting a number every time, so the terms will get smaller and smaller. So when you are adding those terms together, it also won't approach a certain value. That's why the formula has an R in it. Okay, so sum to infinity is just for geometric series, which is why we wrote infinite geometric series. Okay, so sum to infinity will never, you'll never have to calculate, you'll be able to calculate the sum to infinity of an arithmetic one. Okay, so we just need to look at the series. We have 3 over 10, 3 over 100, 3 over 1,000. What am I multiplying by each time, guys? 1 over 10, hey? If you can't see that, you can take the second term divided by the first term, all right? And that will give you the answer. So here you are multiplying by 1 over 10. Multiplying by 1 over 10. So does that satisfy that condition, guys, for us to calculate the geometric or the sum to infinity? Is the ratio between -1 and 1? If it's 1 over 10, right? Yes, it is. Okay. So I'm just going to write here on the side that the ratio is between -1 and 1. You don't have to add that, but maybe just add it for this example. So if you remember, you actually have to check that. Okay. So therefore, for the sum to infinity, all we need to know is A and R. We're not going to sub in an N value, guys, because that's the whole point of this. The whole point of this is that N is going to infinity. All right, if we're adding an infinite number of terms together, what will that sum get closer to? All right, so it's A over 1 minus R. So at the bottom, we're going to do 1 minus 1 over 10. And at the top, what was my A value? 3 over 10. And it's better to write that over 2 lines. Sorry, I didn't think of that now. And then you're just going to type that into the calculator. All right, you're going to type 3 over 10 over, you can work this out in your head, that's 9 over 10, and you can just type it in straight away. You will get a third as your answer. So that means that as I'm adding more of the terms in the series together, it's going to get closer and closer to a third. All right, but not actually reach a third. And does that make sense? Because we're starting with quite a small number already, 3 over 10. And then we're adding even smaller numbers. What's the next one we're going to do? 3 over 10,000, right? Then 3 over 100,000, then 3 over a million, right? The numbers that we're adding are going to be so small that it does make sense that they will eventually add to it. Okay. That is the first question. Number 2. Now, this is a different type of question. But they usually ask something like this: for which values of x will the infinite geometric series, giving us a series converge. Converge. And now guys, they're giving us a series, right? Can we notice from this what the ratio is at the moment? What am I multiplying by each time to get the next term? 1 minus x. Good. Okay, so the ratio here is 1 minus x. And again, from term 2 to term 3, the ratio again is 1 minus x. So even if you can just recognize that and write that down, you'll get it all. Okay, but now they're asking for which values of x will the infinite geometric series converge? Now, if we go back to the note that we wrote, a series is converging if the ratio is between -1 and 1, but not equal to 0. So guys, we are actually going to use this as a formula to calculate the values of x. Because what did we say the ratio is? What was the ratio for this number pattern? Let me just write down. 1 minus x, right? So we're literally going to put 1 minus x there and then solve this inequality. Okay, so I'm just going to write for a series to converge. And converge means for the numbers to get smaller and smaller. Right? The ratio has to be a fraction. So for a series to converge, this has to happen. The ratio has to be between -1 and 1, but also not equal to 0. Because remember, if the ratio is 0, the values aren't going to get smaller and smaller, they're just all going to be 0. Okay? So we found the ratio. We know that the ratio for this series is 1 minus x. So wherever we have an r, we change that. We replace that with the actual ratio, the 1 minus x. And now I'm hoping we remember how to solve this inequality. Right? If you have two parts of it, you need to work out, right, from the inside out. So here, what am I going to do with this 1? I'm going to minus 1 from both sides, right? You remember that? It's positive 1 here. So I need to minus 1 on that side and on that side. So here, -1 minus 1 is -2. And it was negative x there on the inside. Now I also have to minus 1 on that side. 1 minus 1 is 0. And over here, that 1 also is going to become -1 on that side, right? So we're going to have negative x cannot be equal to -1. So we're solving both parts of that kind of condition at the same time. Okay, what happens with this negative? I need to divide both sides by -1, but what happens in an equality when we divide by a negative number? We swap the symbols around. Okay, so this is going to become positive 2. That now needs to become a greater than x. This symbol also needs to swap around, and I'm 0 divided by -1 is just 0. Am I going to be able to leave it like this, guys? Is this correct mathematical notation? The 2 can't come before the 0, right? We have to swap them around. It has to be the smaller number first, but we'll do that now. Let's just quickly check here. I can just divide by -1, right? So x can't be equal to 1. I'll just say therefore, just so that you can see that it's the final answer. The only thing that's left for us to do is to just put this in the correct order. Okay, 0 is smaller than 2. So the 0 has to come first. And then we need to also just change. We're basically swapping that whole inequality over or around. So we need to swap the symbols as well. And we need to say that x cannot be equal to 1. So guys, let's just talk about this quickly. If x is 1, what is my ratio? 1 minus 1 is 0, right? So do you see, that's why we're saying that x cannot be equal to 1, because if x is 1, then my ratio, which is 1 minus x, is going to be 0. Okay, so we have to add that in there. X cannot be equal to 1. And what does this mean? That x here can be any number between 0 and 2, right? Any number between 0 and 2, but not 1. And if that is the case, then this will be a converging. Okay. It's so the second line, this one to here. Yeah, so I've got the one. So this is a positive one here. So I minus 1 from there and from there. Positive one from both sides. Yeah. And then here I move the 1 and I minus the 1. Okay, so guys, those are the two main types of questions that you need to be able to answer for infinite series. The section, they usually ask you for the sum to infinity, and they'll usually ask a question like this, where you need to find the ratio in terms of another variable, and then they'll ask you for which values of that variable does it converge, and then you need to use this. So this is a formula, guys. I'm not entirely sure if this is on the formula sheet. I can fix it just now, but you need to be able to answer questions like this. Okay, another thing that they sometimes do is they'll give you like the A value and the sum to infinity, and you must find R. Okay, so if you're using this formula, sum to infinity is A over 1 minus R, so they'll tell you what A is, and they'll tell you what the sum to infinity is, and you must just solve for R in this equation. Or the other way around, they might give you the sum to infinity and the ratio, and you must find A. Okay, so it doesn't really get much more complicated than that. All right, I'm going to give you two of these to just practice on your own. And then we are actually done, guys, with this chapter. We are supposed to move on to functions on either Monday or Tuesday. So tomorrow, definitely we can use the time to just practice mixed questions all together. And possibly Monday. I'll just check my planner again. All right, so exercise 1.9. We can look at some of the more difficult, like past exam paper questions. Okay, those are the ones that you need to do for tomorrow.